In 1920, the mathematician Srinivasa Ramanujan wrote down a series of equations he called Mach theta functions. They behaved almost like standard modular forms, but they required a specific, mysterious correction term to balance them, a remainder he never fully explained. 28 years later, Richard Feynman formulated the path integral approach to quantum mechanics. His framework relied on a mathematical measure, denoted as script d x of t, that summed the probabilities of a particle's possible trajectories. He wrote the symbol, but left the measure strictly undefined. And almost a century before either of them, in 1859, Bernard Riemann published his hypothesis. He claimed that all non-trivial zeros of the zeta function, the frequencies where prime number phase contributions cancel out, sit precisely on a single vertical line in the complex plane, where the real part equals exactly 1/2. These are historically treated as three separate problems across number theory and quantum physics. They are actually three distinct mathematical projections of the exact same physical geometry. That geometry is the coprime winding torus. Connecting these three pillars provides a literal shape to the equations. It outlines the mechanical structure the universe uses to generate matter. We start with a one-dimensional string under tension. When that string deflects, it opens into a two-dimensional surface. Space itself emerges as the parabolic geometry of that deflection. For a particle to be stable within this space, the wave propagating along this deflected string must complete a full circuit. It has to connect geometrically back to its origin. Fundamental matter particles, like electrons, are spinors. A spinor requires exactly 720 degrees of rotation to return to its original quantum state. One 360-degree circuit only gets it halfway there. It takes two full rotations to close the loop. The simplest topological surface that meets this 720-degree closure requirement is a Mobius torus. It is a closed surface with a half twist, where the inside and the outside are the exact same side. A quantum particle is not a point moving through an empty void. It is a continuous loop bound by the geometric constraints of this twisted toroid surface. A snake eating its own tail, tracing an intricate path along a toroid. In this geometry, specific lanes travel along the surface. They run forward until they hit a 180-degree Mobius half twist. At that seam, their orientation flips, and they travel back in the opposite direction. To understand which lanes are allowed, we use coprime numbers. A number is coprime to a boundary limit if it shares no common factors with that limit. A standard theta function sums all integers. Ramanujan's Mach theta functions do something specific. They act as a sieve. They explicitly sum only the coprime integers, dropping everything else. There is a physical reason for this restriction. On a closed torus, winding paths based on composite numbers hit subharmonic nodes. They complete a subperiod and terminate early. They fail to connect point A back to point A. In 2002, the mathematician Sanders Wagers proved the exact structure of Ramanujan's mysterious correction term. That remainder is the explicit accounting of all those excluded, broken composite paths. Decades before quantum field theory was formalized, Ramanujan had written down the exact boundaries of the Feynman path integral. The Mach theta function tracks exactly which trajectories the universe rejects, isolating the domain of geometrically closed paths. On a straight number line, prime numbers appear chaotic, but mapped onto a circle, their distribution becomes rational and periodic. If you step around a circle in fractions of exactly 2 pi divided by a prime number, that path is guaranteed to eventually close precisely on its origin. This creates a primordial hierarchy. Each successive tier of physical complexity in the universe is built by multiplying the next consecutive prime number into the geometry. The hadronic sector, the environment of quarks and gluons, operates on a geometry governed by the number 30. This is the product of the first 3 primes, 2, 3, and 5. When we apply the coprime filter to this mod 30 boundary, exactly 8 numbers survive. Those numbers are 1, 7, 11, 13, 17, 19, 23, and 29. These 8 mathematically isolated paths correspond directly to the 8 independent polarization modes of the gluon. Look closely at their arrangement. They form 4 perfect mirror pairs, like 1 and 29, or 7 and 23. Each pair balances its counterpart exactly across the topological geometry. Any winding number that shares a factor with 2, 3, or 5 shatters against this mod 30 limit. They cannot form stable loops. The allowable mass states and internal structures of all nuclear matter are strictly constrained by the geometric arithmetic of prime numbers. This same principle scales down to the electron shell, which operates on a smaller geometric limit known as mod 12. Mod 12 is derived by taking the prime factor 2, squaring it, and multiplying by 3. Applying the coprime filter to 12 leaves exactly 4 surviving lanes: 1, 5, 7, and 11. These form 2 mirror pairs, 1 and 11, and 5 and 7. They represent the forward and return winding directions of the electron path. But unlike the perfectly balanced hadronic lanes, these specific pairs are offset from each other by exactly 4 units. Because of this geometric asymmetry, their wave functions cannot cleanly cancel out. This offset forces a topological collision. Where the 4 winding lanes intersect, their failure to neutralize forces the interference pattern outward into space. The shape generated by that specific 4-lane collision is identical to the classic 4-lobed geometry of the d orbital. Looking at this data table, the formula holds across the entire sequence. The number of coprime mirror pairs exactly dictates the lobe count of the atomic orbital. The natural moduli sequence of 4, 8, 15, and 21 perfectly reproduces the geometric shapes of the s, p, d, and f orbitals. The distinct shapes of chemistry are not abstract probability clouds. They are the rigid, unavoidable consequence of prime-based topological collisions. Returning to the Riemann hypothesis, for over 160 years, mathematicians have visualized Riemann's critical strip as existing on an infinite, flat, two-dimensional plane. We must map that strip onto its actual topology. The plane rolls into a cylinder, and a half-twist locks it into a continuous Mobius band. The azimuthal direction around this torus is the real axis. The poloidal phase, the winding around the tube itself, is the imaginary axis, denoted by gamma. A Riemann zero is the specific physical frequency where the interference of these coprime winding paths perfectly and destructively cancels out. We find the natural modular circle for any zero by taking its gamma value, multiplying by 2, and rounding to the nearest integer. For the very first Riemann zero, located at 14.135, that calculation is 2 times 14.135. That rounds to exactly 28. Mod 28 is the specific geometric threshold where the mod 12 electron geometry interfaces with the mod 30 nuclear geometry. Understanding the physical structure of these numbers removes the abstraction of the Riemann hypothesis. It turns a problem of pure mathematics into a statement of mechanical necessity. There is one final geometric rule governing the system. The mathematical centroid of any coprime residue group must inherently sit at exactly n divided by 2. Because these numbers form perfect mirror pairs, perfect destructive cancellation can only occur if the paths are flawlessly balanced around that specific centroid. Because the cancellation point is strictly locked at n/2, the topological mirror axis of the entire toroid is forced onto the line where the real part equals 1/2. The critical line is simply the physical seam of the Mobius band, the exact location where the winding paths flip to chirality. Ramanujan mapped the surviving lanes. Feynman traced their integral paths through space. And Riemann discovered the exact frequencies where their geometry falls completely silent.